Tessa. I am in a tenure track at the Department of Physics, University of Trento. And today, at the annual Radiation Research Society meeting, I'm interviewing Dr. Scott Welford. Can you introduce yourself?
Certainly. I'm Scott Welford. I'm an associate professor at the University of Miami, Department of Radiation Oncology.
Okay, so Scott was one of the speakers in the session I chaired, so I should know everything about what you do, but as the people that are listening to this, they don't. If you can please explain to us in very simple words, since I'm a physicist, so not in your field, please make me understand what you do.
Sure, I'd be happy to. I was very privileged to get a NASA award to study how space radiation affects the carcinogenesis process. And as you know, we brought many animals to NSRL for you to help us with. We were studying a hematopoietic malignancy model in which we have an MLH1 deficiency, and this is relevant because MLH1 is deficient in many normal, healthy people as they age, particularly of concern for NASA, potentially astronauts when they go into space. But
the space radiation wasn't your background to start with, so it's something you arrived to. What was your background?
Absolutely. So I think of myself as a radiobiologist sort of by accident. I was really trained as a cancer biologist. Okay. And then I joined Amato Giacch's group at Stanford, and Amato is well known in the radiobiology field. He's famous for studying hypoxia. So I got into tumor hypoxia, and then I was a radiation oncology person from then on. And so then accidentally we saw this opportunity for NASA and space radiation, because obviously what we know about terrestrial radiation is very interesting and cool, and then we think about space and we know nothing about space. So that got us to the next level.
Okay, so in this we're similar, like the physics that you can apply for radiotherapy, you can apply to space too. Is physics then?
Well, we should hope so.
Yes.
Except that you tell us that we can't.
So when was the first RRS meeting you joined?
The first RRS meeting was probably I think it was in Hawaii, not in the past few years, but about 8 or 9 years ago, I guess. And who could resist to come to the RRS meetings in these phenomenal locations?
Okay, so if you have to think about, compared to other conferences that you attend to, the fact that you have are they as multidisciplinary as this meeting is, or less or more?
I don't think anything is as multidisciplinary as the Radiation Research Society. And that's why our field is great, right? We have to continue to innovate, and we have such great strengths in all the individual disciplines. And when we put it together, we develop collaborations and learn something new.
How many times do you see a physicist sitting together with a radio-oncologist and talking about their work? Yeah, true, fair enough.
Not too often.
So, what would you see your research in the future will be more in space, more into the radiotherapy or radio-oncology, or both, or?
Well, I think that in today's funding times, you need to be opportunistic, take advantage of doors that are open to you. And I think that's one of the great parts of our field. There's a lot of different applications for what we learn. So I'm very keen on continuing our space radiation studies. I'm keen on continuing our cancer biology, radiobiology studies. And when we can marry them, that would be the best situation. And I think that, for example, what we've learned about our high LET radiation in space, this is now coming down to earth, so to speak, as we come up with ways to implement carbon therapy and, at the very least, proton therapy. So what we can learn from these studies does have a direct translational impact on what we can do for patients in the future, or so we hope.
Okay. Can physics help? Since I'm a physicist, I mean, I don't know, maybe chemistry can help too, but I know it's not my playground.
I think physics is essential because, much as it seems like all they have to do is push the button, obviously there's much more that goes into all these aspects of treatment planning and pure radiobiology questions that really pure biologists like myself do not fully appreciate. So I think these collaborative interactions are really fundamental to opening new doors.
Okay, but in your department, are there physicists or other people out of the discipline, or it's mostly biologists?
Well, like any real clinical radiation oncology department, you need physicists. They need to come in, and even for medical physics, which is perhaps less exploratory than space radiation physics, that's an essential part of the clinic. And so I think good, strong departments like the one we have in Miami depend on physicists who are there, who also partake in research, who are interested in developing new treatment approaches, and even in the context of small animal radiation, where we do lots of our experimentation, we need to develop new machines to properly model what's happening to patients in the clinic. So.
I swear this is not an advertisement for physicists. It's more like how can we be useful to other disciplines. So let's say that if you would have an infinite amount of funding, what would you do?
Well, I
mean, with research, not with your private life.
I would go to Mars, right? That's what it's all about.
You go to Mars? Okay. Yeah, so how do you think, for example, okay, now since you brought up Mars, how do you think your research will really help into Mars exploration?
Well, I think the basis of our research is in line with some of NASA's goals, which is, at this point, to some degree, risk estimation. You know, we don't really know what's going to happen to astronauts because we don't understand the biology of the space radiation impacting on human biology. So a lot of the questions right now are understanding what the risk is. And then the next question is, what can we do about it? So our studies now are, frankly, identifying, I think, a new risk that was not previously appreciated. There's been a lot of studies that have been done, and as we progress in the field, we come to look at our studies and say, well, we should have done that a little differently. And that's been true for animal studies forever, that we generally are trying to extrapolate what we can get from an animal, from a mouse model, into a human, and there's a lot of differences. Like for one, mice live 2 years, not 80 years. And so this question of latency from when you're exposed to radiation and what may come, is that going to happen in a mouse into the same time frame? And we can't really model that because we're not going to make mice live 80 years and then, of course, couldn't perform our experiments reasonably.
Okay.
And so our studies tried to incorporate an age-related defect in humans and bring that into the mouse and see if we could, again, extrapolate in a better way what might be the risk to those animals. So I hope that what we've learned is that we need to perhaps consider these aspects of DNA repair functionality in astronauts and add that to the risk model. And then we can perhaps come back with interventional strategies. Now, whether that means we need to screen astronauts and choose them wisely based on these effects, or whether that means we need to come in therapeutically, maybe even prophylactically, and say, you've got this defect, this could be a problem, let's do something ahead of time. So I think that's where we're going in terms of mitigation and what we've found.
Okay, but the fact, now I ask maybe a stupid question for biologists, but definitely maybe not for physicists, like you're taking a mouse that, aside from the aging problem, is also much smaller. So like all the organs are much closer, so our organs are much further. How this, maybe this, so how this must be taken into account when you go from a model, you study something on a mouse and then you model on the human, or is it, or is not, maybe? Well,
so this is a physics problem, right? I mean, the physicists tell us that every cell in your body will be traversed, what is it, one time on the way to Mars and something like that. Well, a mouse is this big and a human is this big, so that calculation certainly needs to come in, and presumably either the field size at NSRL needs to be made smaller, or we need to take that into account in terms of dosage and how much actual energy is being deposited. It's certainly different in a human than it is in a mouse.
Yeah, I'm thinking about, for example, like radiotherapy, more radiotherapy than space. I mean, in space, basically, you are surrounded by radiation, so more or less isotropically, everything gets hit. But in radiotherapy, you can get, I mean, radiation far away from the tumor. Now, if you're far away, is not so far away, you will get a lot more dose there. Sure. So that was my train of thought.
So the off-target effects in
exactly.
a mouse are likely to be much greater than in a human. And sure, I think that depends on our delivery systems, how fancy we get, how sophisticated we can be, but also in proper modeling. So I think that, for example, when prostate is irradiated in a human, there are lots of studies that look at secondary cancers due to the bladder or the rectal radiation. There's also studies in lungs, and it actually turns out from SEER data that the rate of incidence of secondary cancers is very similar. And so this tells us something about the biology of the off-target effects. This tells us something about the biology of the tissue that is being irradiated. And certainly in a mouse model, we should consider that as well. Now, perhaps the field size is smaller in mouse. I mean,
Sure.
when we go through IFF procedures, the size of the tumor we can let grow, maybe 2 centimeters, that may be the size of the tumor which is first observed in a person. So there's a scale involved for sure. And the best we can do is to make proper judgments based on the data.
Okay. So at the next meeting, if there is something that was missing in this meeting, what would you like to hear in terms of topics that you think was missing? If there was any, maybe it was perfect.
Well, that's an interesting question. I think that there's a trend in these meetings, that in one meeting you go there and there's a lot of space biology, space radiation, space physics, and then people may swing back and say too much space and they go away from it. So it sort of goes back and forth. I think that the quality of the talks has really been outstanding. If I could make a suggestion to the committee, I would suggest that more ECI faculty members, ECI individuals get to give talks, which is always a conundrum because a lot of people come to see the big people speak, and I think we have to look toward the future, and there has to be a good balance between giving the younger folks a chance to become big and famous and appreciating.
I can assure that the organizer have been working on that, so this is definitely going to change. Yeah, so, okay. And what about in terms of topics, like specific topics? Is there anything that you think is missing?
Well, as a hypoxia biologist, I have to say we've gone away from hypoxia.
Okay. Okay.
So I think that bringing that back in would be a strength to the program. And certainly with the immunotherapy trends that are coming out now, there's a clear connection between hypoxia and immunotherapy.
Okay, so one last question, since we're done, we're free to go. So since we have to have a conclusion, and I'm the interviewer, so I don't have to the conclusion. You have to make a conclusion. Send a message.
Oh, the message, I would echo the message which has been coming out for a number of talks at this meeting, which is that collaboration is absolutely the key to our future. We have a funding model which is so individualized, and really these meetings are our opportunity to get to know other people and develop collaborations. That's going to be the way to breakthroughs in the future, and I think physics and biology is a great place to start. But certainly when we think of fields as well, that the space biology people and the clinical radiation oncology people, we all need to get into the room and talk. That's the purpose of this meeting, and I think it's been a great meeting so far and should continue to be in the future. So
I want to thank Scott for taking some time to be interviewed, and I'll see you next meeting.